Welcome to my video course on RAMS engineering for railway systems. We are going to explore the ultimate framework that literally tames the chaos of infrastructure failures. Have you ever really thought about how these massive, incredibly complex railway networks manage to move millions of people safely and on time, day in and day out? Well, let me tell you, it absolutely does not happen by accident. It happens through meticulous, foundational engineering. Okay, here's a quick look at our agenda. We'll be starting with the core concepts of railway RAMS, looking at how it drives competitiveness, diving into safety design and the math of uptime, and then wrapping up with engineering resilience and some real-world case studies.
Section 1. Introduction to Railway RAMS, the core framework. So, to kick things off, we really need to take a macro view of this framework. It's what transforms a bunch of mechanical components into a highly reliable service. And look, RAMS is not just some corporate buzzword, okay? It is a highly meticulous engineering discipline that governs literally every single aspect of a modern train's lifecycle. It stands for reliability, availability, maintainability, and safety. Now, in the old days, railways might have treated these as, separate operational headaches to deal with after the system was already built. But a systematic RAMS approach forces us to bake these four pillars directly into the inherent product design from day one. It's essentially the DNA of the entire railway system.
Section 2. Driving quality and competitiveness, the bottom line.
Let's talk about the economics, because in modern railway systems, RAMS is a completely critical decision-making factor. Why? Because it directly influences your quality of service and your total cost of ownership. High RAMS performance ensures that rail traffic is safe, timely, and cost-effective. Think about it for a second. If your trains are constantly breaking down, your total cost of ownership just absolutely skyrockets from all those emergency repairs, and naturally, your quality of service tanks. By maximizing punctuality and capacity through RAMS, we directly enhance the competitiveness of rail transport against other sectors like road or air. It's literally what makes trains the most viable, sustainable, and reliable alternative we have for the future.
And what we're looking at here beautifully illustrates what I like to call the trinity of impact. Safety, punctuality, and revenue are all driven entirely by system availability. Moving beyond just, basic failure prevention brings us to real service assurance. Availability is at the absolute center of everything. Because if your signaling system isn't available, you're forced to rely on risky manual interventions, which obviously compromises safety. If it's not available, trains get delayed, which destroys punctuality, and of course delayed trains being a massive hit to your revenue and passenger throughput. Even the most incredibly reliable system becomes totally useless operationally if repair times are too long and availability drops.
Section 3. Systematic safety by design. No accidents.
We really must hammer this fact home. True safety relies on proactive lifecycle management, not reactive after-the-fact repairs. A systematic RAMS approach is absolutely essential, because safety is achieved by design, not by chance. You can't just build a train, throw it on the tracks, and hope for the best. Safety has to be engineered into the very circuitry and software of the system itself, requiring fail-safe technologies and rigorous lifecycle processes to protect passengers and the public. So when things inevitably do fail, because they fail in a way that protects human life.
So how do we actually do that? Well, using rigorous standards like EN 5126, engineers systematically eliminate hazards through these exact lifecycle processes. It all kicks off at step 1, with hazard identification. Next, we implement fail-safe criteria. A really classic example of this is a default-to-stop behavior. If a signal loses power, it doesn't just turn off and leave everyone guessing. Gravity or relay literally forces it to drop to a red stop position. But, engineers also have to juggle some pretty complex operational rules. For instance, automatically stopping a train if an emergency is detected sounds perfectly safe, right? Well, what if that train is currently on fire inside a tunnel? In that specific scenario, stopping is incredibly dangerous. And that is exactly why Step 3, establishing redundancy architectures, and Step 4, validation and field monitoring, are so critical. It's this continuous, ongoing loop to ensure the design actually holds up to real-world safety needs.
Section 4. The mathematics of uptime, calculating reliability.
All right, let's dive into the hard math for a second. This visualizes the crucial mathematical balance between mean time between failures, or MTBF, and mean time to repair, MTTR. Availability is essentially MTBF divided by the sum of MTBF and MTTR. On one side of the scale, you've got reliability, how long a system runs without breaking down. On the other side, maintainability, how incredibly fast you can fix it when it does. Now here is the secret sauce for high-density networks. Reducing repair time is actually the fastest and, frankly, the most cost-effective lever you can pull to increase your availability in continuous operations.
Let's look at how this math plays out in reality. This subsystem analysis is a great example. It proves that solid-state electronics totally excel, while physical mechanical components, like point machines, become our biggest vulnerability. Look right at the top at electronic interlocking. It has a massive mean time between failures of 100,000 hours and a tiny repair time of just 2 hours. That gives us 99.998% availability. But then scan down to the point machine at the bottom. It's physically moving heavy steel tracks, dealing with friction, dirt, weather, the whole shebang. Its MTBF is only 2,000 hours. And actually, look at the repair time. It takes 6 hours to fix. That drags its availability all the way down to 99.7%. And let me tell you, in the world of high-speed rail, that missing fraction of a percent, that equals massive, cascading delays.
Section 5. Engineering resilience and redundancy. Fixing the weak links.
So the big question is, how do we engineer our way out of those physical vulnerabilities? The answer is implementing hot standby configurations and modular hardware. This lets us instantly switch to backup systems the second a failure happens, completely preserving our availability metrics. If one CPU or power supply fries, the system detects it and switches over automatically to a hot standby. The passenger sitting on the train literally doesn't feel a thing. The train just keeps moving safely along. Combine that redundancy with modular plug-and-play parts, and you've suddenly slashed your repair time from hours to mere minutes, radically shifting that uptime equation we were just talking about.
But we don't stop there. By coupling redundant design with predictive IoT sensors, we are basically waging an all-out war on repair times. We aren't just sitting around waiting for things to break anymore. IoT sensors can detect a weird vibration anomaly in a point machine or the slight degradation of an LED signal way before it completely fails. We use reliability-centered maintenance to aggressively prioritize our most critical assets. And practically speaking, storing those critical modular spares locally at stations rather than at some depot 50 miles away means we completely bypass the logistical delays that artificially inflate downtime. The ultimate goal here? Consistently hitting repair times of under 30 minutes.
Section 6. Real-world case studies. Theory in action.
Let's wrap up by looking at the real-world stakes of all these engineering choices. Take a look at this dramatic contrast. On one hand, you have a catastrophic 20-day network outage caused by legacy fragility. On the other, the 99.97% availability achieved through modern dual-redundant servers. Back in 2015, a fire at Itarsi Junction destroyed the relay interlocking system. Because they lacked geographic redundancy, that single point of failure caused a massive network outage that lasted over 20 days. 20 days of zero availability. Now, flip that over and look at successful modern implementations like the Delhi Metro. By utilizing dual redundant servers, modular design, and auto failover, they consistently hit greater than 99.97% availability. It's an incredible illustration of the high cost of fragility versus the immense, tangible value of engineered resilience.
Which really leaves us with a pretty massive question about our commitment to long-term design over short-term chance. Are we just, patching things up so the trains can barely limp through the daily commute? Or are we truly adopting this RAMS engineering discipline to guarantee a flawless, fail-safe, and highly competitive service for the future?
Thanks, we can see you in next video.